Physics 2211 Lab 1 report by Jacob Bernstein. The purpose of this lab is to explore the motion of an object moving at constant velocity and effectively modeling that very motion based on the fundamental principles surrounding Newton's second law. This lab accomplishes the object above by demonstrating both Newton's second law and, by mathematical definition, the momentum principle, through the observation of the movement of a constant speed electric skateboard along a fixed axis. This lab also corroborates the soundness of both aforementioned fundamental physics principles by generating a computational model that compares the expected motion of the skateboard to the observed motion of the skateboard, and then subsequently compares that to the observed linear motion. The two main principles of which this lab is based on are as follows: Newton's second law with relation to both velocity and momentum. And while we won't delve too deep into either of these equations, the main idea that we'd like to extract is that since the net force acting on the electric skateboard is zero when the skateboard is in constant motion, the final velocity of the skateboard will essentially be equal to the initial velocity of the skateboard. It's important to note, however, that we make the key assumption that the net force in this system is equal to zero when it, in fact, cannot perfectly be equal to zero, and we'll revisit this later on. This is the example of the experiment we conducted, and it's important to note that the system is the electric skateboard, the surroundings are the floor and the wall it bumps into, and the initial condition is simply the initial velocity of the electric skateboard. I found it helpful to note that this is a picture of the software called Tracker that was used to plot the lateral position of the electric skateboard against time. The computational model relating the skateboard's lateral position with relation to time is developed here in GlowScript, and some important aspects to note is that it took 5.7 seconds roughly for the skateboard to travel 3 meters, and it was traveling about 0.521 meters a second at constant velocity, and the net force acting on the object was zero. Next up, we have the observed lateral position of the electric skateboard as a function of time, which we saw in the experiment, and then the computed or predicted lateral position, which is modeled in red. Now, obviously, the computed model is linear because the electric skateboard is moving at a constant speed, and then the observed model is slightly nonlinear, which is a function of a few different sources of error, which I will touch on briefly. Possible sources of error are as follows. One being the manual error that was generated when I was tracking the electric skateboard's position using the software. The next is the influence of external forces on the motion of the skateboard. Obviously, the system is not perfectly, the net force is not perfectly equal to zero due to friction, but we negated that for simplicity's sake. The potential variable speed of the electric skateboard, meaning when I was controlling the speed, I could have pressed too hard or too soft. And then the nonlinear motion, which is not too much of a factor, but the skateboard could have skewed minimally left or right, which would produce error. Now, conclusively, if we flip the x-axis and instead of being positive x, the motion of the skateboard was along the negative x-axis, none of the fundamental figures nor takeaways would be altered. It's just the sign of the motion. And then to answer the second question, while the net force is zero, it doesn't necessarily mean that there are zero forces acting on the object. And in this instance, gravity acts as a downward force, normal force is upward. And although we've deemed friction and air resistance to be negligible, they are not exactly absent from the system. Thank you for watching, and to sum it all up, the model I created is consistent with the observations because the motion of the electric skateboard reflects an equilibrium situation where the net force is inherently zero.